Okay, so today we're going to cover Chapter 6, Section 3. 2 more segments of triangles. Today we're going to talk about medians and altitudes. So let's go ahead and take a look what a median is. So a median of a triangle is going to be the segment that goes from the vertex to the midpoint of the opposite side. Every triangle has 3 medians. And then the point of concurrency, which will be on the next slide, where all 3 medians are going to meet, is called the centroid. And that's what we're going to cover on the next slide. However, this picture, the red line, is only 1 median. I'm going to go ahead and draw in the other 2 medians because remember, you have 3 vertices, so you also have 3 medians because they're going to come out of the vertex and then they're going to go across the triangle and look for the median of the side across, or the midpoint of the side across from it. So I don't have any coordinates. I don't have a ruler. So I'm just going to sort of guesstimate where my midpoint is. So right now I have the median that's going from vertex C to midpoint D. D is the midpoint of AB here. I'm now going to find the midpoint of AC, so I'll say it's about here, and then I'm going to draw in the median. It goes from vertex B, it goes across, and it hits the midpoint. So this is going to split AC into 2 congruent pieces. So I could even call this point E. E is the midpoint of AC, and it splits AC into 2 congruent pieces. I'm going to do the same thing and draw the median coming out of vertex A. I need to find the midpoint of BC. I could say my midpoint's probably about here. I could call this F. And then I'm going to draw the median coming straight out of A. And it hits the midpoint at point F. Again, the midpoint splits this into 2 congruent pieces. So your medians are going to go from the vertex to the midpoint of the side opposite. So all of these red are the medians. And then you had the original that was drawn in the figure. So you have 3 vertices, so we're going to have 3 medians. So the point where the 3 medians all meet is this point right here in the middle. And this point where they all intersect is called the centroid. And the centroid, again, is the point of concurrency of the medians of the triangle. The centroid is always located inside the triangle. Another name for a centroid is called the center of gravity because it's going to be the point where if we had a triangular region or a triangular shape, and if I were to try to balance that triangle on a stick or on a pencil, soon as I find that centroid or that center of gravity, that triangle will balance. Now, just to recap what we did yesterday, so far we've learned 3 different points of concurrency. So just to recap, yesterday we talked about perpendicular bisectors, and we talked about their point of concurrency being the circumcenter. Remember, the circumcenter is either located inside when it's an acute triangle, it's located on the triangle when it's a right triangle, and it's located outside the triangle when it's obtuse. It's just a review of yesterday. The other thing we talked about were the angle bisectors. And for this one, its point of concurrency is called the incenter. And just like the centroid, this one is always inside the triangle. So again, start making yourself a little study guide to help review all of this. I've actually added a slide at the end of these notes that summarize the different segments. But again, start memorizing for Tuesday because we have a quiz on Tuesday on 6.1, 6.2, and 6.3. Everybody good on the little summary here and the location of the centroid, always inside the triangle. And again, remember the centroid is where the three medians all intersect. So it's the point of concurrency of your medians. The centroid theorem states that the centroid of the triangle is going to be 2/3 of the distance from each vertex to the midpoint of the opposite side. So in this figure, the medians of triangle ABC are all meeting at point P here, and point P is our centroid. And what the theorem is stating is when we come out of a vertex, so for example, A, coming out of A, the length from A to P is always going to be 2/3 of the length of the entire median. And then when we go from P to E, this will be 1/3 the length of the entire median of AE. And we can do this for each of the medians. So coming out of C, this piece would be 2/3. And then going from the centroid to the midpoint would be the 1/3 piece. Same thing for B. Coming out of the vertex, hitting the centroid is the 2/3 piece. And then from the centroid to the midpoint is the 1/3. So again, just to recap, so when we come out of the vertex, to the centroid, that's going to be 2/3 of the length of the whole median. And that's what the theorem states. And then after from the centroid to the midpoint, that's going to be 1/3 of the whole median. Now, if you're familiar with the fractions 2/3 and 1/3, if you were to try to convert those to decimals, they actually turn into repeating decimals. 1/3 decimal equivalent is 0.3 repeating. 2/3 is 0.6 repeating. So because of that, I do not want you to convert these fractions to decimals. I want you to work with them as the fractions that are given. So we're going to keep it 1/3 and 2/3 and then work the problem that way. So we're going to work with them as fractions. This is so far out of the two points of concurrencies that we've already talked about. This one doesn't create any congruent segments. This one is going to be 2/3 and 1/3. If you remember the perpendicular bisectors and the angle bisectors, they created segments that were equidistant. So this one does not. So let's try an example of this one. So in triangle LMN, S is the centroid. So this is the point of concurrency of my three medians. Remember, from this centroid to the vertex, this little piece here is going to be 2/3 the length of MP. This would be 1/3. Over here for the L, From L to the purple point is 2/3. And then from the purple point to R would be the 1/3. And then same thing coming out of vertex N. This would be the 2/3 piece. And this is the 1/3 piece. So now let's go ahead and see if we can answer the two questions. So here it says that the length of RL is going to be 21. So the length of this whole median, RL, is 21. So 21 is the length of the entire median of RL. It wants me to find the length of LS. So LS is going to be 2/3 the length of that whole thing. So to answer part A, the equation I'm going to set up is that LS is equal to 2/3 the length of RL. So I'm going to replace what I know. I know that the length of RL was given to me as 21. When I multiply fractions, whenever I multiply a fraction by a whole number, I can add a 1 to the denominator. Now, if you choose to just multiply it the way it is, do 2 times 21, get 42, and then have to go back and divide that by 3, what's a lot better is to simplify diagonally. And this is a 4th grade skill where you learned how to multiply fractions, okay? And if you can simplify diagonally, it definitely helps the process here. So I'm going to change the 3 and the 21. I'm going to change this to a 1, and I'm going to change this to a 7. And now I'm just multiplying 7 times 2, I get 14, 1 times 1, and I get 1. So my answer for the length of LS is going to be 14. Now, let me just add to this question. If instead they had asked me to find the length of RS, I can set this up the same idea, except for RS, I can see is the 1/3 portion of this. So what I could do is multiply RL by 1/3 to find the length of RS. So RS is equal to 1/3 times 20 over 1. Again, I like to simplify. And the length of RS is equal to 7. Now, technically, if I was asked to find this, if I knew already RL was 21 and I already found the piece of LS, I could have also subtracted 21 minus 14 and gotten the length of RS that way as well. So these are all little ways that you can go back, do the problem another way to check your answers. All right, next we're going to find the length of NQ. So this is a different median that we're going to work for. So that median is up and down straight, this vertical line here. And this time in the beginning of the problem, they told me the length of SQ. SQ, this little piece here, I was told is equal to 4. So again, I'm going to use my 1/3, 2/3 thing. So I know for part B, what I can do here is I know that 1/3 of the length of NQ is going to be equal to SQ. So I'm trying to find NQ. So if you'd rather say NQ is X, so you don't have 2 letters, you could do that. But I'll just leave it as an NQ. I was told that SQ equals 4. Here we go with our algebra skills. Think of this as just being your variable. So 1/3 times the length of NQ. So to undo multiplication, I'm dividing by 1/3. So if you think about when you divide fractions, you're doing keep, flip, change, or stay, change, change. So really what I'm doing is multiplying both sides by 3, or the reciprocal of 1/3. And my answer here, this simplifies. So NQ is equal to 12. If it asked me to find the length of, say, NS, again, I could just take 12, subtract the 4 that was given to me, and the length of NS would be 8. I could also have multiplied by 2/3 and then multiply by its reciprocal. Either way there. Okay, so the next slide, we'll do another example. Here's a real world example. It says a sculptor is shaping a triangular piece of iron that will balance on the point of a cone. At what coordinates will the triangular region balance? So what we're looking for is this center of gravity or the centroid. So again, we're going to draw in all of our medians and find where they all intersect. So remember, the medians go from the vertex to the midpoint of the side across from that. So what I need to do is calculate 3 different midpoints. So the first thing I'm going to do is find the midpoint of this side here. So I'm going to add my x's, x1 plus x2, divide by 2, y1 plus y2, divide by 2. I end up getting 16 over 2 and 13 over 2, which gives me 8. 16 divided by 2 is 8. 13 divided by 2 is 6.5. So I'm going to go ahead and graph this median, or this midpoint. So it's at the order pair 8, 6.5. So it's right here. Again, the median goes from the midpoint to the vertex. So from this vertex, I'm going to draw the median in. Next, I'm going to look for another midpoint. I'm going to find the midpoint of this side here. Take the 2 coordinates, add the x's, add the y's, divide that by 2, 18 divided by 2, 9 divided by 2. The midpoint of that side of the triangle is the order pair 9, 4.5. So I'll place a point on that midpoint. And again, draw it to the vertex. So that's my next median. Got to do one more midpoint and draw in that median. So I'm going to do the midpoint of this side. So again, I'm going to take 6 plus 8, divide by 2, 6 plus 2, divide by 2, 14 divide by 2, 8 divide by 2, and I get 7,4. So graph that one, draw in that median, and you can see your point of concurrency is this order pair where they all 3 cross, and this is going to be the order pair 8, 5. Now, when you're doing this, you need to be nice and neat and graph them carefully. Now, I'm going to show you a trick to find this centroid that is not in your book. So if you're not paying attention right now, then the way that you're going to do this on the test is to do what I just showed you. Okay, so here's the trick. The easier way would be to take the 3 x's of each of your vertices. So I'm going to add 6 plus 10 plus 8, divide those by 3, take the 3 y's, 6 plus 7 plus 2, divide that by 3. I end up getting 24 when I add 6 plus 10 plus 8. And when I add 6 plus 7 plus 2, I get 15. And then now, when I simplify that, I get 8, 5, which is my centroid. So a nice little trick that always works. However, if you weren't paying attention, then what you're going to do is the book's going to teach you the long way. Yes. Another way that you could also find this centroid is whenever you could also take in any of the medians. you could have found the length of it by doing the distance formula, and then you could multiply that by 2/3 and then add that number to your ordered pair. It's a lot more work, but it is another way to do it. So just be aware of that and just apply your centroid theorem. All right, now we're going to talk about altitude. So we got another group of segments. So the altitude of a triangle is going to be the perpendicular segment that's going to go from a vertex to the line containing the opposite side. Now, this is where it gets tricky because you're thinking, oh, wait a minute, my perpendicular bisectors are right angles, but the difference, the perpendicular bisector hits at the midpoint. This one is just the perpendicular segment that's going straight down. It may not hit the midpoint. Sometimes it does. Sometimes the altitude and the perpendicular bisector could be the same segment, but not always. Okay, so this is again where your sometimes, always, or nevers are going to come into play. So every triangle has 3 altitudes, just like every triangle has 3 medians and 3 perpendicular bisectors and 3 angle bisectors. And just like the perpendicular bisector, these can be located either inside, outside, or on the triangle. So again, this is where your memorization is going to come into play. You got to memorize these locations. Now, when you probably did this in middle school and you were asked to find areas of triangles, a lot of times you were always looking for the height because the formula for area of a triangle is base times height times 1/2 or base times height divided by 2. And you always had to look for the height and it was always next to a right angle. So another name for the altitude of a triangle could be the height of the triangle. Pretty good? Let's go on. The point of concurrency of the altitudes is called the orthocenter. So the orthocenter is going to be the point of concurrency where all of the altitudes meet. So in this picture, all of the red lines here are our altitudes. So AF, BD, CE, they're all meeting at the point of concurrency, which in this picture is point G. So all of the red lines in this picture are your altitudes. Yes. All right, so let's try to locate an orthocenter. So again, just like before, we're going to graph these 3 ordered pairs first. So I'm going to graph X. It's going to be located at the ordered pair -3, -4. Y is located at the ordered pair -3, +4. And Z is at the ordered pair 5, +4. Once I connect my points, I notice that 2 of the sides of my triangle are one side's horizontal, one side's vertical. So that's a clue to me that this is a right triangle. Because I know that always horizontal and a vertical line, when they intersect, they're going to intersect to form perpendicular lines. Now, what you're going to find when you have a right triangle, that the 2 legs here of the right triangle are going to be the 2 altitudes, or 2 of them. And then I just have to draw on the 3rd one. So this leg right here, YZ, is actually an altitude because it's coming in here out of vertex Z, and it's the perpendicular distance or the length. Then if I go from vertex X, the perpendicular segment is the leg XY. So when you have a right triangle, the 2 legs are 2 of the altitudes. Now we just have to draw in the 3rd one. So the 3rd one, again, is going to come out of the vertex Y, and then it's going to go down to the side across. And again, it doesn't have to hit at the midpoint. So I'm just going to draw a perpendicular segment out, and this would be your third altitude. Notice all three altitudes are all meeting at point Y. So your orthocenter, when it's a right triangle, is always going to be the location of the right angle. So this is my orthocenter. And it's the order pair, -3, +4. It's always going to be located at the right angle vertice. To put that singular, the right angle's vertex. Or the vertex of the right angle. Does that make sense? Next slide again is just summarizing the location of the orthocenter. So again, the location of the orthocenter, just like the perpendicular bisectors, which is the circumcenter, these depends on the type of the triangle. So when it's acute, it's in. When it's right, it's on. And when it's obtuse, it's out. All of the red lines in this picture are all our altitudes. So the black lines are the outlines of your triangle. Let me do it in highlight, I guess. So the black ones are the edges of or the sides of our triangle. And again, here's my right triangle, and right here is my orthocenter. It's where the two legs meet. And then over here, when it's obtuse, notice all of these altitudes are meeting outside of the triangle, way up here at P. So the red lines are all the altitudes, the black lines are all the edges or the sides of your triangle. And then the last slide is a nice little summary of these 4 segments that are within your triangles. They're points of concurrency. So the first column has the name of the segment. The second one gives you an example. Remember, there's 3 though of each. Then the third column has the point of concurrency. And then the next column, the fourth column, it's either describing the theorem or different properties of that bisector or whatever the segment is, whether it's making congruent segments, whether it's 2/3 of the length. So it's just describing the property. And then the last picture has all of them drawn in. So a nice little summary of your 3 segments. So that concludes all the information that you're going to need for Tuesday's quiz.